Okay, let's go over the quiz. Number 1, trapezoid ABCD is congruent to trapezoid YZWX. I have to match up the corresponding angles here. Okay, so if I say ABCD like most of you did, angle A corresponds with angle Y. I know that because angle A is between this 90-degree angle. By the way, angle A looks like it's also 90 degrees, but it's between this 90-degree angle and the 140-degree angle. So if I go mash that up on the other shape, angle Y is between this 90-degree angle and the 140-degree angle. Okay, so ABCD, YZWX. You didn't have to say that. You could say CBAD as long as you said WZYX. Multiple different answers you could give for this one, but you got to match up. Notice I didn't use any commas, no parentheses, nothing like that. Okay, just matching up the corresponding angles. That's how I write my congruent statement. Speaking of corresponding angles, number 2 is incorrect, or at least the student got it incorrect, because they said both figures have 4 sides and the corresponding side lengths are equal, so they're congruent. Now that statement's true, but there's more to it than that. To be congruent, the corresponding side lengths have to be equal and the corresponding angles have to be equal. Uche?
I put this the shape is congruent, but then you said the same.
Are you sure you weren't talking about the angles? No, they're not congruent. You're right. I probably should have taken a half point off. I was skimming through there and I was looking for you to say that the angles were the same.
I put that, but you put the same. I said that. You wrote the same.
Yeah, they have the same corresponding angles. Yeah, this statement that you wrote right here, that the shapes do not have the same corresponding angles, is why you got it right. Now, you shouldn't have said what you did on top because they're not congruent. Okay, but I was skimming through and looking for that exact statement that the corresponding angles should have been matched up. They should have been the same. They weren't the same. Harrison?
So number 1, I put commas in between the letters.
I didn't count it wrong. Just know you don't have to.
On a test, would you count?
No, we don't typically do that though. We just write it like triangle ABC. We don't put commas between them. If you said that it's a different shape, you're right, but you didn't say what made it different. What makes it a different shape is the fact that the angles have changed. When the angles change, it changes the entire shape. Okay? We talked about that yesterday when we talked about similar shapes, how the side lengths are proportional, but the angles are still the same. Okay? Change the angles, you've changed everything. A lot of you didn't use the word. I had a lot of people write that the angles have to be the same. I gave you credit for it, but that's not technically right. The angles don't have to be the same. The corresponding angles have to be the same. For example, to say that the angles have to be the same for these 2 shapes to be congruent makes me think that to be congruent, all angles have to be equal, and that's not true. The only 2 angles that have to be equal are C and W, and Y and A, and D and, oh, I'm sorry, Y matched with A and D matched with X, thank you, yeah. And B and Z, those are the only ones that have to be equal. I don't mean for them to all be equal, just the corresponding ones. Caleb.
For that one, do you have to start at a specific letter? Could you go like C, Y, X, W?
You sure could. The only thing you can't do is jump from Z to X. But as soon as you pick a point, you can go this way around it, or you can go this way around it. You just can't cut through the shape like that. You can't go from Z to X or from A to C, something like that. Yes?
Are you recording?
I am recording. Okay, thank you. All right, number 3, 4, and 5. You got half a point for the arrow notation and a half a point for having the correct coordinate. Number 3 has been translated 2 units left, which means you're subtracting 2 from the X coordinate. It's been moved 5 units up, which means you're adding 2 to the Y coordinate. And when you do that, you should get -7 and -3. Number 4, when you reflect across the Y-axis, you take the opposite of the X coordinate. There's no flipping. You're just taking the opposite of the X coordinate. So that -5 is going to become +5. The -8 stays the same. 5, -8. And for number 5, a 90 degrees clockwise rotation takes the opposite of the x coordinate and then it does flip it. So -5 becomes +5 again, but then now you are going to flip it and it's going to go where the y coordinate should be. So -8, 5. Interesting. I'll do it later. Never mind. I don't like how dark that highlighting is. Normally I would have changed it, but I guess I didn't notice. On number 6, this is a translation. They've moved it right 5 units and moved it down 3 units. So I'm going to move every single point over 5 to the right and then down 3. Over 5 to the right, down 3, down 3. You did not have to put J prime, K prime, L prime, but you did have to graph the 3 points and make a triangle out of it. Number 7, a reflection across the x-axis. The x-axis, again, your horizontal axis. Everything that was above is now below. And that's why when you reflect over the x-axis, you take the opposite of the y coordinates, because now instead of positive y coordinates, they're all going to be negative y coordinates. The x coordinate doesn't change at all. Caleb?
So you won't take off, and if we don't go like J prime, K prime.
No, I wouldn't. Max? 1 point apiece. If you missed one coordinate, you missed, if like, let's just say you graphed it incorrectly, you missed half. If you missed 2 or more coordinates or the whole thing was wrong, then you missed the whole thing. So if you would have graphed it, for example, over the y-axis instead of the x-axis, it caused all 3 coordinates to be wrong, which means you missed the full point, just because we probably weren't paying attention. Number 8 was a 180-degree rotation. Now, a 180-degree rotation takes the opposite of the x-coordinate and the opposite of the y-coordinate, and that's it. I don't need to think of it in terms of moving it 90 degrees and then moving it 90 degrees again. I don't need to think of it like that. There's no flipping. 180-degree rotation just says, okay, so -5, 4 is going to become +5, -4. Right there. Where'd my prime unit go? Or let's just go back. Yeah, let's just go back. Okay. And same with K. Instead of K being -2, 3, it's going to be +2, -3. Instead of L being -4, 1, it's going to be +4, -1. We don't flip. We just take the opposite of both coordinates. Questions on the front? Number 9 on the back side, they give you Q, R, S, T, and then Q prime, S prime, T prime, R prime. Skipped over R prime. And so you'll see that the coordinates have definitely been flip-flopped. So it's some sort of 90-degree rotation, but they took the opposite of the y coordinate before they flip-flopped them. And so the opposite of the y coordinate when you flip-flop becomes a 90-degree counterclockwise rotation. Have to have the word rotation, have to have 90 degrees, have to have counterclockwise. Yes?
For number 10, if the first prime number, if it was a 90 degrees counterclockwise, would that put it in quadrant 4?
It would still put it in quadrant 3. Wait, are you saying start with this one?
Yeah.
Yeah, then it would put it in quadrant 4. Yep. And instead of A pointing to the left, A would be now pointing down. You're thinking reflection. It'd be 90 degrees. So instead of looking like that, it's going to look like this. Yeah. Yep. So for number 10, the 2 transformations, and so this is it's not. I'm not asking you what did they do from here to here, and then what did they do from here to here. I'm asking you what did they do from here to here, and then from here to here, because this is single prime and it goes from single prime to double prime. So they obviously reflected this one over the x-axis to get here, and then for this one they moved it 180 degrees. You don't have to specify a direction, because either way, 180 degrees is the same. So 180-degree rotation. And then for the bonus, reflection across the line, y equals x. Remember that when you reflect across this line, you just flip-flop them. Okay? Much like a 90-degree rotation, but you don't take the opposite of anything. You just flip-flop them. So these 2 have been flip-flopped, 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 and flip-flopped. I wouldn't be able to tell if I just looked at y and y prime, but when I put all of them together, I can see that they flip-flopped all of them. And so that's the reflection over y equals x. Yes?
Would it be the same if you put x?
It wouldn't be that, well, it wouldn't be the same because this y equals x is a line. And that line is written in slope-intercept form with the y-intercept being 0 and the slope being 1. So it looks like this, okay? I think the reason you might have missed that one is I don't think you put reflection. Yeah, so you're missing multiple parts to it. I think that's why. That's why I didn't even give the partial credit, because you had to have the reflection as well. One thing we talked about in our IXL that we did, our geometry IXL, they asked you to reflect across the line y equals negative x, which looks like this. Who can tell me what you're supposed to do if you reflect over that line? Caleb?
You flip them, but you take the opposite of the line.
Yes.
Or the x.
Both. Yeah. So if it's reflecting over this diagonal line y equals negative x, then you do take the opposite, both of them, and flip. Challenge question. What one transformation could take the place and replace these two transformations?
What was the question?
What one transformation could replace both of these in one step? Claire?
180-degree rotation.
180-degree rotation. Because in a 180-degree rotation, you take the opposite of both. Well, if we reflect over the x-axis, you take the opposite of the y. Reflect over the y-axis, take the opposite of the x. 180-degree rotation does both that in one step. Yep. So 180-degree rotation could replace both of these combined. Jace?
Can you reflect over the origin?
You can only reflect over a line.
Okay.
So because the origin's a point, I would say no. Now you can rotate around a point, but I can only reflect over a line. So you gotta have some line that's your mirror.
Would there ever be like on the IXL that's like rotate 180 degrees over the origin? Would there ever be an actual point?
Yeah,
Okay.
they could, and that would stink.
Yeah.
And we haven't done that. The only point other than the origin that I've had you rotate around was one of the vertices, one of the vertices of a triangle or something where you just like rotate it on that point. If I said, here's a triangle and I want you to rotate it around that point, you could do it, but the arrow notation that I've shown you is not helpful in the slightest. Like you could still rotate it, it'd be up here somewhere, and you'd have to figure, okay, it went down and up, and okay, now I'm going to go this way, and you could still do it. It's just would be a lot more visual and a lot less arrow notation, and you won't have to do that on your test. Questions on the quiz? Retakes tomorrow, SLT. All right, so we need to start our 2.7 notes. Let's get those out. Dilations. The only type of non-congruent transformation we'll talk about is a dilation, which is a form of similar transformation. It's going to result, the resulting image is going to be enlarged or reduced, but everything was done proportionally. We learned yesterday that similar figures have the same corresponding angle measurements, but those corresponding sides are proportional. They've been changed, but not randomly. They didn't just add 6 to everything. They multiplied by 2, or they multiplied by half, or something like that. So a dilation is a transformation in which a figure is made larger or smaller. I suppose you could multiply by 1, but if you dilate something by 1, it doesn't change. It stays congruent and nothing happens. Therefore, it wasn't transformed. So a true dilation is going to change the size. Now, when I think of dilations or dilating, I think of our pupils being dilated. Okay, which means they're getting much bigger or smaller. So like, for example, if you've ever been in a dark room like a movie theater and then walk out and your eyes have to adjust, That's because what's happening is your pupils are so enlarged because there's not much light, so it's trying to take as much light as possible. And then all of a sudden they're overexposed to light when you walk out of that dark room, and your pupils being much larger are taking in that it actually hurts your head. And so it's really bright, and so your pupils then adjust and they get small. Okay? Same thing happens if it's really light out. Okay? So if I'm driving outside without sunglasses, because there's so much glare off the sun, my pupils are going to get smaller because I don't need all that. Okay. And then when I walk into a dark room, it's pitch black. I mean, like even a room that's not pitch black, I can't see anything because my pupils are so small, they need to enlarge. We had this thing, I don't know if you guys did this when you were in elementary school, we had this star gazing thing, this blow up tunnel that we had to climb through, and then they projected all the constellations inside of it.
Nope.
You guys were deprived as kids. So we did this every year. And so they'd show us like Betelgeuse, which is that like red star and all that stuff. And so when we walked in, we were told we had to close our eyes. And so as I got older, and I did this 3 or 4 times, I started to question, why do I have to shut my eyes? So I didn't. And I couldn't see anything for about 5 minutes. He's pointing to things. I can't see anything. I can't see the pointer. I can't see anything because when I left my eyes open like that, it took a while for my eyes to adjust. And so I couldn't see in the dark as well as everyone who had shut their eyes. So that's why they had to. It wasn't like they were trying to trick us or something. It was just, no, they're trying to get us to where we could see.
Well, how did your eyes adjust when it was darker in your head?
Dark in my head.
Oh, was the lights on in the room? Was the lights on in the room?
Yes.
Oh, okay.
Before we went in. Before, yeah, that's, yeah. Levi?
You know, airplanes, when they're taking off, the lights go off, so your eyes adjust to the darkness in case there was an emergency.
Ah.
The lights turned off,
And you can see the way you're supposed to head out for what you're supposed to do for an emergency. I didn't realize that. Makes sense though.
You go to an eye doctor, don't you get your eyes dilated?
I have been once to an eye doctor. I think you do,
Yeah.
right? Don't you? So.
I don't know.
All right, so the image is going to get larger or smaller in respect to a point called the center of dilation. Okay, and that point is not usually a point that's on your shape, although it could be. It could even be inside the shape, but a lot of times it's outside the shape. Okay. So it says, tell whether the blue figure is a dilation of the red figure. Well, is the blue figure, does it look like the same triangle, but it's been made bigger or smaller?
No.
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 Okay, so this isn't a dilation then. What is it?
Translation.
Translation. It was only moved. It was moved, but it wasn't dilated. Yeah.
Can we just put no?
Sure. What about example B?
Yes.
That is a dilation. And so the center of dilation, this is kind of cool. Why in the world it won't do that, I don't know. Close enough. They should, if I could get my line to actually touch the edge of that triangle, which I tried and it will not. But you see how they all intersect right there? That point is the center of dilation. So this, it says the blue figure is a dilation of the red figure. So the red figure was the original. They've shrunk the triangle down with respect to this point so that it's still the same shape, but smaller. Okay. What about example C, Devin?
No.
No, what was it?
A reflection.
Good. Yeah, reflection. And then what about example D, Ashton?
Yes.
That one has been dilated. Yep, that's right.
Also,
Well, wouldn't it be to the red to the blue?
Yes.
It can go down.
Red to blue. Mhm. So this one, did it get bigger or smaller?
Bigger.
Because it goes from red to blue, it got bigger. Yes.
I tried to log in a Big Ideas to like have my homework done and ready,
Uh-huh.
and it's not loading.
Okay. Well, don't worry about it right now.
Well,
Oops, sorry, I went to the wrong one. Trying to show you the point of dilation, center of dilation here. It's not going to be exact because my lines aren't perfect. But it's really cool to see that. It's almost like you can see it project. It's like three-dimensional now. And so our center of dilation is right there, very far away from the shapes. I feel like I'm in art class. I'm like, is it perspective? Is that what they call that? Where like things that are closer are bigger and things that are farther away are smaller. I didn't get a good grade in art, so. Okay. Yeah, it was the only class I got a C in high school.
Wow.
I did, yeah. If I would have taken it my senior year instead of my freshman year, I probably would have cared more about it. But yeah, it's kind of what I warned you guys about. Like I just didn't really notice. I didn't really know how your GPA affects your grades or how your grades affect your GPA. So like I was like, oh, I'm not good at art. So I was okay getting a C in it. And then I spent the next 3 years trying to make up for that bad grade. So I don't want you guys starting off your 8th grade year with a bad grade. That's what I would have been warning you guys about. All right, it says these two triangles are similar. Compare the coordinates of the red triangle with the coordinates of the blue triangle. So we need the coordinates of the red triangle. Madison Davis, I'm going to ask you to give me the coordinates for point A, Callan, point B, and Riley McLaughlin, point C.
Leah Warland, Rebecca McGuire, Carson Dewey, please come to the office. Thank you.
Olivia Sefton, I'm going to ask you for point Q. AJ Finney for point R, and Haley Kraus for point S. All right. Madison, what do you have for point A? Good. And point B, Callan? And point C, Riley?
Montasia Conwell, please come to the office. Montasia Conwell, please come to the office.
What'd you say? Good. Okay. And who had Q, Olivia? Okay. And R, AJ?
2.
Okay. And Haley, S?
1.
All right. Now, I want you to compare, because I didn't tell you which of these was the image. So we're gonna go both ways. We're gonna pretend for right now that the red figure was the original one and that it got dilated to the blue figure. So if it gets dilated to the blue figure, did it get bigger or smaller? Smaller, okay. So the way that we say that, it actually, we're gonna say it was reduced. So I'm gonna use the letter R to remind myself that it was reduced in size. And then what are they multiplying all of the X coordinates and Y coordinates by to reduce that, Jace?
1/3.
By 1/3, exactly. Now, if you were thinking to yourself, they just divided them by 3, you're right. But the way that we do dilations is we always think in terms of multiplying. So instead of thinking divide by 2, we think multiply by 1/2. Instead of divide by 3, we say they were multiplied by 1/3. Instead of saying they were divided by 4, we say that they were multiplied by 1/4. Okay. Now, if I go from blue to red, then if the blue was my starting shape, I'm not sure why I'm changing colors, then it was enlarged, and I'm going to put an E to show that it was enlarged. And what did they multiply all the blue coordinates by to get to the red coordinates, Elise? 3. So you could say it was enlarged by 3, which is the reciprocal, the exact opposite of what we said before. We always think when we're dilating a shape in terms of multiplying. What did we multiply the coordinates by? Don't think divide, think multiply. In a dilation, the image is similar to the original figure. The ratio of the corresponding side lengths is called the scale factor. In the example we looked at here, the ratio, our scale factor was 1/3. This ratio of 3/1 reduced to just 3. Just like slope's a ratio. If I said the slope was 6/3, I'd reduce it to 2. If I said it was 5/1, I'd reduce it to 5. Ratios can be reduced. Okay. So we'll be using some fractions as our ratios here. We can also write those as decimals as well. And so when it says scale factor, that means every single point was multiplied by that same number to result in that similar shape. Haley, I'm going to ask you to bring the book up here now. I warned you yesterday. All the way up here. All the way. Thank you. To dilate a figure with respect to the origin, so Jace, we're specifically just doing the origin, although we could do any point, just the origin. We're going to multiply the coordinates of each vertex by a scale factor called K. K is typically the variable chosen for a scale factor. I have no idea why. It just means that we're multiplying everything by the same number, and that number is K. Do you remember when we did our direct variation? Did we? We did direct variation. We may not have time. There's a 7th grade lesson and an 8th grade lesson. I might have just given you the 8th grade lesson. In the 7th grade lesson, they say that the direct variation formula is y equals kx.
Yeah. Oh, yes, I remember.
Do you remember something like, okay,
No.
because you hadn't learned that m was the slope. So a direct variation is actually y equals mx because the b value, because it goes to the origin, doesn't have to be written. And so in 7th grade, you would have said y equals kx instead of y equals mx. I don't even think we had time for that lesson. You might just remember that from last year. But that k means we're multiplying x by that value. So k is always a multiplication. And so here's the arrow notation that we're going to use. If I need to multiply, or if I need to enlarge or reduce the coordinates, I'm still writing it as a scale factor, a multiplication of k. So if I'm dividing, I still need to think of it in terms of multiplying. And so if I multiply the coordinates by 2, the way that I write my arrow notation is I'd put 2x comma 2y. What if I'm dividing by 2? Elise? It would be, yes, 1/2 x comma 1/2 y. Yes?
Did you do x over 2 and then y over 2?
No, because you're thinking of it in terms of division. And we're thinking, what number are we multiplying?
No, like to divide. Like the 1/2 x could have, instead of being the 1/2.
You're changing it from, when you write x over 2, you're changing 1/2 x into a division problem though. And it would give you the same answer, but the k is the number that's being multiplied, not divided. So it'd have to be 1/2 to answer your question. Yes, it would give you the same answer, but I have to have the 1/2 as my k. So if I'm enlarging the shape, I have to have what kind of k value, Jace?
Oh, I was gonna
Oh.
ask something else.
Go ahead.
For like k is multiplication.
Yes.
What's division?
There isn't. You mean like a variable for division? There isn't one.
Z.
Sure. Ashton,
How is, like, why are the 2's to k's again?
because k represents the number that we're multiplying the coordinates by. It's called a scale factor. Remember how yesterday we said factors are the two numbers that you multiply? Product is the answer. Factor means multiply. So when we think scale factor, we have to always think multiplication. Now, what number do so let's start with this. What number would I multiply by and the shape not change?
1.
1. So if I want the shape to get larger, I have to multiply it by a number that's larger
Then 1.
than 1. AJ. Yes, your arrow notation, you just write 2x comma 2y or 3x comma 3y. If I want to reduce it, it's got to be smaller than 1. But it can't be too small. It can't be negative. So it's got to be between 0 and 1. If you multiply by a number between 0 and 1, like 1/2, it's going to get smaller. Or a third or a fourth or a fifth, it's going to get smaller. Clear?
If you did it by 0 though, wouldn't it just go
It'd vanish. It would, yeah, it would entirely vanish because, well, it wouldn't vanish. Your answer would be 0, 0, 0, 0, 0, 0. You'd get 1 point on the origin. So it wouldn't entirely vanish, but the shape would go away. It'd just be a point on the origin left, which is the point we happen to be dilating in respect to. So then you just get that dilation point. Okay. Determine if the scale factor would enlarge or reduce the shape. Multiplying by 2.
Enlarge.
Multiplying by 2/5.
Smaller.
Yeah, 2/5 smaller one. It's going to shrink it down. Multiplying by 1/3. Reduce it. Multiplying by 1.
Same.
Yeah, nothing's going to happen. I guess S for same. It's going to stay the same. Nothing's going to happen. It won't be dilated. You won't even be able to tell anything happened to it. 0.5. Yeah, same as a half. 5/4. Enlarged. Yeah, so even though it's a fraction, it's an improper fraction, larger than 1, so it would actually increase the size of the shape. So here's your arrow notation. Just like we've had for every single shape, we have arrow notation here. To enlarge a figure, multiply by a number greater than 1. To reduce a figure, multiply both coordinates by a number between 0 and 1. And that number is the K number. So if I'm writing arrow notation, I would, whatever number I'm multiplying by, that goes in front of the X and in front of the Y. If I just write it in front of the X, it shows that you're only changing 1 coordinate, which would change the shape. So, I don't know if you've noticed, but I keep copying and pasting the same shape. This is the same triangle we've done for all of our transformation notes. I'm going to enlarge this one, because it's bigger than 1. I'm going to dilate it with a scale factor of 1.5. So, for my arrow notation, if you want to use 1.5, you can. If you want to use 3/2, you can. But I have to put what number I'm multiplying by, and I have to write that in front of both the X and the Y. Caleb.
So would that make M prime 3/4?
Not 3/4, but 4.5.
Yeah, 4.5.
So I'm multiplying it. Think, you know, if you don't want to use a fraction, I understand that you can write 1.5x comma 1.5y, but think that you're multiplying it by 1.5. What that does is basically you're not quite doubling it. Imagine if you were doubling it, but only increasing by half that much. Okay, so like for 3/2 here, if I doubled 4, I'd get, or if I doubled 2, I'd get 4. Right between 2 and 4 is the number 3. If I double 3, I get 6. Right between 3 and 6 is the number 4.5. Okay, so if you multiply 3 by 1.5, you get 4.5. What about 4? When you double 4, you get 8. And what's right between 4 and 8?
6.
When you double -1, you'll get -2. And what's right between -1 and -2? Good. Yeah. And if you're completely lost right now, just times by 1.5. That's all we're doing, okay? What's 1 times 1.5?
2.
1.5. What's -3 times 1.5? Good.
Couldn't you also just multiply the number by 3 and divide by 2?
Yes.
Yeah.
Yep. Very similar to what we did when we worked with spheres. We had to multiply by 4/3. Do you remember that? 4/3 pi r cubed. We multiplied by 4 and then divided by 3.
Yes.
Yeah. You don't have, seem like you have a good memory of that.
No, I don't like that.
Didn't like that. All right. So then I'm going to graph these. My M prime is going to be at 3, 4.5. And then, oops, I'm trying to copy and paste that so I don't have to keep drawing it. And then 6, and then -1.5. And then 1.5, -4.5. It did. Yeah, it did. And the cool part is when I show you here, if I draw the lines, you can actually see that just like I did at the beginning of the notes, they all intersect at the origin because the origin is my center of dilation. So if I did it right, I should be able to draw a line through the corresponding angle points, the corresponding vertices, and it should all intersect right back there at the origin, because that's the only point that we're going to make for our intents purposes in this chapter. That's the only point we're going to use as our center of dilation. If I multiply by half, is it going to reduce or enlarge it? Reduce it. Okay. Half of 2 is, half of 3 is, half of 4, half of -1. Half of 1, half of -3. Okay, good. So my new M prime is going to be at 1.5. My new N, sorry, I forgot to copy and paste that again. There we go. My new N prime is at 2, -1/2. And my new P prime at 1/2, -1.5. Yes. And again, I could draw lines that all intersect there at the origin. Maybe I should write, this is my new, I think it's pretty intuitive, but that's my P prime, my N prime, and then my M prime right there. The shape, the direction of the shape doesn't change. It's not rotated or reflected at all. It's just literally shrunken. Now, instead of drawing the shape with the given scale factor, we're going to look at 2 shapes, one regular, one image, and we're going to find out what the scale factor was. Okay. Now remember, the red for all of our chapter, the red shape has always been the starting shape. And if you forgot that, you can tell because they've listed the prime units here with the blue shape. So I know that's the image. So it started off red. It was enlarged. So I know it's got to be bigger than 1. To find out what it was, all you have to do is look at 2 corresponding vertices. What's the coordinate of A? 0, 2 goes to 0. What did they multiply by? 3. And that will be true no matter what. B was 2, 2. It went to 6, 6, right? So they just multiplied by 3. So I just have to pick 2 of the vertices. Use a color that doesn't show up on the coordinate plane already. Okay, so now let's look at maybe x and x prime. Starting at x, so this was reduced. The coordinates for x are what, Devin?
The coordinates for x would be -2, -4.
Good.
8.
Good, yeah, they're counting by 2 on the x and y axis. So this is -4, 8. And then what's the coordinates of x prime? Devin?
-2, 4.
What did they multiply 4, 8 by to get to -2, 4? Yes, yes. Don't think of it as dividing by 2. Think of it as multiplying by 0.5 or by half. You could say either one of those. It says, how does the dilation change the area of each figure? Let's go back to example A. To find the area of a triangle, I have to multiply the base and height and then divide by 2. So multiply the base by the height. What's 2 times 2? Divide by 2. So the area of that triangle is 2. The area of this triangle, multiply the base, which is 6, by the height, which is 6. What's 6 times 6?
18.
Divide by 2.
18.
Okay. So does dilating by a factor of 3 make the area 3 times bigger?
No.
No, it made the area 9 times bigger.
Is it because,
Why is it?
is it because 3 to the power of 2 is 9?
Correct. And we'll talk about this tomorrow. Because when I take the area of a shape, it's 2-dimensional, correct? So it's 3 squared times bigger. Think about this. Not only did the base get 3 times bigger, but the height got 3 times bigger. So when I do base times height, this is 3 times bigger. This is 3 times bigger. That's 9 times bigger now. Okay, I didn't just change I didn't just change one dimension. I changed both dimensions by 3. And so that's why it's 3 squared or 9 times bigger. Good. Okay. And similarly, the area of the red rectangle is 4 by, is that 7? No, I'm sorry, we're counting by 2s here. It's 8 by 2, 4, 6, 8, 10, 12, 14. What's 8 times 14? 7? 112. So the area went from 112 to the blue, which is just 4 times 2, 4, 6, 7. What's 4 times 7? 28. So when we reduced it by half, did the area go down by half? No, it went down by a half squared, which is a fourth. A half times a half is a fourth. So it was 1/4 times bigger. Technically smaller, I know what you're thinking, but if that's what I'm saying is it's you'd be multiplying it by a fourth. So it's actually smaller. Let's go ahead and finish these. I'm not going to let you go out there until that line dies down anyways. You have 3 points. I've already written them down there for you. It says dilate the trapezoid with respect to the origin by a scale factor of 2. And then we're going to rotate it 90 degrees counterclockwise. So let's scale it by 2. What do I write on my top arrow? Elise. You got it. If I'm dilating by 2, I write 2x comma 2y. Okay. Nuche, what's A prime going to be?
That's going to be -4, negative.
Okay. And Caroline, what's B prime going to be?
-2, 2.
Okay. And Claire, what's C prime going to be?
0, 2.
And Levi Rum, what's D prime going to be?
So that would be 0 and 2.
Negative 2. There you go. Okay. Now, when we rotate it 90 degrees counterclockwise, Ashton, what's our arrow notation going to say?
-yx.
Good. Opposite of the y and flip it. Okay. So take the opposite y and flip it. Ashton, what's A double prime?
2, -4.
Good. George, what's B prime going to be? Got it. Jace, what's C prime going to be?
-2, 0.
Caitlin, what's D prime going to be? Got it. And last one. The red figure is similar to the blue figure. Describe the sequence of transformations from the red, in which the blue is the image of the red. So yes, from red to blue. Now, I know it's been dilated. I know it has to have been dilated, but I don't know what it was dilated by. Let's make the shapes go the same direction first. So what would I do in order to get that, the red's the original. So what would I do to get the blue shape to flip the same way, Levi?
90 degrees clockwise.
Not 90 degrees clockwise. That would make it point this way. Counterclockwise would make it point this way. I want it to go from pointing up to pointing down.
So reflection.
Reflection over which axis? X. An x-axis reflection. If you're thinking 180 degree rotation, that is going to move it. It is going to point it down, but it's going to move it over to quadrant 3. We don't want that. Okay. Because we're dilating in respect to the origin, so we need to get it lined up with the origin. So from the first transformation we could say here is it was reflected over the x-axis, And so if I unreflect it over the x-axis, and I'll use purple for this, that would make it look like this. Not really good. That's better. And then what did they dilate it by then?
2.
By 2?
Yeah.
Are you sure?
Yes. Wait.
Because that's wrong.
Oh, no.
Claire, not Claire, sorry, Caroline,
3.
not 3.
Are you sure about that?
Remember, it went from red
Oh, red.
to blue
Okay. 1/2.
by 1/2. By 1/2.
Red.
Yeah, so and that's why the order, that's why the instructions, it wasn't extremely clear because you list the blue first, but it says the blue is the image of the red one. That means the blue is our final product. And so they shrunk it down. And so it has to be now the way I write that, because remember, we have to be specific. We can't just say it was dilated, but we would say that it was dilated, or you can abbreviate that, dilated by 1/2. Or you could say dilated K equals 1/2. There's multiple ways you could show me, as long as I know you use that word dilation, or at least the abbreviation for the word dilation, and then what the scale factor was. Okay. That's it. Use your restroom break. Come back. We'll get some homework done. Haley, you can have your book back at 2:30 p.m.
Okay.